Hi, welcome to our talk. Yeah, so today we're going to be talking about how to measure your Kubernetes components. Briefly, my name is Han Kang. I'm a software engineer. I lead the cluster ops team at Google, which is a part of the broader GKE API machinery team. In open source, I contribute to both SIG API machinery, instrumentation, and I actually wasn't aware that I still had a Twitter, but Elana correctly deduced that it was exactly the same as my GitHub handle. And this is Elana.
Yep, I'm Elana Hashman. I'm a principal site reliability engineer at Red Hat. I'm currently one of our tech leads on the Azure Red Hat OpenShift team. I'm also a member of SIG Instrumentation since 2018. If you want to tweet at me, my handle is ehashdn, and my GitHub is ehashman. So, what are we going to cover today? I'll start out by introducing how instrumentation works in Kubernetes. And then Han will talk about the various components of the Kubernetes control plane and dive into more detail on their instrumentation. Then we'll both cover some real-world debugging examples using the metrics and tools we've introduced. And last, I'll talk a little bit about metrics usability and the SIG instrumentation roadmap. So let's start from the beginning. How does Kubernetes instrumentation work? Kubernetes components integrate with Prometheus, a time series-based open source monitoring and alerting toolkit. Your instrumented software will use the Prometheus client to export metrics in Prometheus format on some endpoint, which then can be scraped and stored in a time series database. Typically, your scraping mechanism is the open source Prometheus server, but there are other cloud and vendor tools that can scrape Prometheus metrics, such as Stackdriver or Azure Monitor. All Kubernetes binaries are instrumented using Prometheus clients and export Prometheus metrics by default. And so, as soon as you set up a metrics sync, you can collect metrics on your cluster health without any additional configuration. So what do Prometheus metrics look like? Each time series has a name, a series of labels with values, and an overall value. In this example, our time series is called up. It has a label of job with label value Kube-apiserver, and label instance with label value API1, and the overall time series value is 1, presumably because our API server is up. Time series names and labels let us query and drill down into our data. Prometheus metrics will typically also have some associated help text, which describes what the metric means, as well as a type annotation, which indicates the data type of the time series value. There are 4 metric data types in Prometheus. First, counters, whose values are monotonically increasing integers. As their name suggests, counters are typically used to count a number of occurrences. For example, number of requests or number of failures. Gauges represent values that can increase or decrease. They are a very flexible metric type. You might use them to track payload sizes or record latencies or represent uptime, like in our example time series here. Summaries and histograms are more complex data types that allow us to track distributions of data and determine performance at a given percentile. Summaries are pre-calculated for specific percentiles, whereas histograms are served in bucketed form for later aggregation. Summaries are more accurate and efficient, but can't be aggregated across many data sources. For example, if you wanted to calculate the 99th percentile latency of pod launches across all kubelets in a cluster, you would need to use a histogram, not a summary. From a combination of these simple data types and labels, Kubernetes developers have built metrics for each component that we can collect to help us measure the health of our cluster. When I quantify the quality of service of a cluster, I like to consider the dimensions of availability, latency, and capacity of my service, as well as any errors. What does this look like in practice? As an example, let's consider some of the metrics available from the Kubernetes API server. If we want to measure our API server's availability, we can look at the uptime series, as we saw in the last slide, which is a gauge with a value of 1 when the server is online and 0 when it's offline. To get an idea of request latency, we can use the API server request latency seconds histogram, which allows us to examine the distribution of server request latencies. To collect data on our API server's capacity and throughput, we can take a look at the API server request total counter. From that metric, we can derive request rates and get a picture of load distribution. Last, we might want to collect some data on errors in our API servers. Many things can go wrong, of course. And what's gone wrong is not always going to be obvious from a single metric. But here's a counter. API server dropped request total, which we probably want to stay close to 0. We can derive the rate of dropped requests from this, and perhaps build an alert if that rate exceeds 0 for some period of time. So I've talked a little bit about what Prometheus metrics Kubernetes exports, but not how to use them. Without diving into this too deeply, I want to cover some use cases and open source tools that you can use to aid in measuring cluster health and debugging. The Prometheus query language, PromQL, can be used for metric analysis and aggregation, and we'll see some examples of it in action later in this talk. But where do we actually write our queries? If you're using a Prometheus server backend to prototype and for one-off queries, you can use the Prometheus web UI, which is deployed alongside the Prometheus server. Once you've figured out some stable, useful queries, you can display the aggregated data in permanent dashboards. Grafana is an open source dashboard and graph editor that's capable of accepting Prometheus as a data source. If you want to be able to alert on your queries, you can configure alerting rules and set up the Prometheus Alert Manager to process them. And last, if you find you need programmatic access to your data or you need to perform arbitrary queries, you can also fetch metrics from the Prometheus server in JSON format. Now, an individual metric is never going to tell you the whole story on your cluster. Lots of different issues may manifest the same way. For example, there are many reasons why a node might go offline, but in most cases, you will see that node's uptime metric drop to 0. A single symptom is not enough information to form a diagnosis. Maybe the node went offline because its workload got too high and it can't report back, or maybe there was a networking issue. Metrics can give us a good idea of how something is failing, but not necessarily why. By exploring multiple metrics and data sources, we can pinpoint the specifics of a failure and figure out the why. Even if metrics don't show the whole picture, they can guide us to what we should look at next. If a node is down, we can take a look at system performance metrics and see if there are any anomalies that might have led to the node dropping offline. We also don't need to limit ourselves to metrics. Other tools we might use for cluster observability include log files, audit logs, cluster events, etcd dumps, and more. But in order to use our metrics most effectively, we need to understand the context in which they were produced. Without a mental model of how a Kubernetes cluster works, it's much harder to pick up on the breadcrumb trail they're leading us down. To illustrate this, Han made me this chart of a Kube-apiserver that keeps going online and offline. Hey, wait a minute, is this a Grafana chart?
It is indeed a Grafana chart.
Now, seeing this chart, you may be worried, not just about the pun. You might ask me, doesn't everything in a Kubernetes cluster depend on a functioning API server? This looks pretty bad. And sure they do, but it turns out our application's doing just fine, because Kubernetes architecture does not necessarily require a functioning control plane in order for the data plane to work. There are more questions you should be asking me. Is this the only API server in the cluster, or are there multiple running in a high availability configuration? Is this metric for an individual server, or for the load-balanced FQDN across all API servers? The more systems context that we have, the better we can understand these signals and use them to assist us in debugging.
So in order to do that, we're going to try to pry apart the control plane just to get to the core of what we can actually observe. Let's start with a little bit of context. In Kubernetes, we basically have a hub and spoke model of network communication, which means that point-to-point interaction is not allowed between components. In principle, the components of a control plane are neither aware nor allowed to communicate with each other directly. All of their interaction must be mediated by a hub, which in our case is going to be the Kube-apiserver. On a slightly orthogonal dimension, we have the kubelet. Let's briefly go over the kubelet model. There are 3 icons. So on the left, you'll see the node. In the middle, the kubelet. And on the right, the pods. The nodes I like to think of as representing some sort of computational resource. These can be VMs or even physical machines. On the right are pods, which encapsulate a single deployable unit in Kubernetes. This can consist of a container or multiple containers. In the middle, there's the kubelet, and that's the daemon which runs on the node. It is primarily responsible for making sure that the pods which are supposed to be running are in fact up and healthy. In most master configurations, and by master, I mean a node which is running the components of your control plane, these master configurations are going to have a kubelet running your master components as pods. And because of this, each of the master components is going to expose a health endpoint, which the kubelet can monitor so that it can try to restart the pod if it becomes unhealthy. Specifically, this is known as liveness probing. Because this health checking model is such a common and pervasive way to set up a control plane, all of our master components will have these health check endpoints, and we can rely on this. We can also rely on the fact that we're going to have some metrics in the shape and the format that Elena just described, and we're also going to have logs. And while we are always going to have this baseline for inspecting the control plane, not all Kubernetes components are going to be equally introspectable. Some of them are going to be way better than others on what they can tell you about your cluster or its operational state. Specifically, what I have in mind are two master components, the Kube-apiserver and etcd. And by no means am I saying that the controller manager and scheduler are not important. They clearly are. You can't have a functioning Kubernetes control plane without these things. But the fact remains, if you look at controller manager logs, you will only ever see controller manager things. If you look at scheduler logs, you will only ever see scheduler things. But what about the API server? Well, since the API server is the hub of the control plane, every single component interaction must go through the Kube-apiserver to communicate. The Kube-apiserver centralizes those interactions. So if you want to go digging for things which have happened in your cluster, this is going to be a terrific place to start. So how do components communicate with the API server? Well, the Kube-apiserver provides a RESTful HTTP API that the components will interact with. And we can actually examine this by adjusting the verbosity of any kubectl command. So if you set the verbosity of a kubectl command to 9 or 10, you can see you can see the output, which will let you copy and paste and directly curl from the terminal. But that's just the surface of Kube-apiserver introspectability. The fact is, the Kube-apiserver is so central, increases the value of introspecting it. Since all component interactions will go through this RESTful API, we can see those interactions in our API server logs. So if we set our log verbosity high enough, we're going to be able to see all of the requests that go through the API server. This makes the Kube-apiserver logs a terrific source of data to mine, since unlike the controller manager and scheduler logs, where we only see controller manager and scheduler things, in API server logs, we will see controller manager things, scheduler things, and basically anything else that interacts with the Kube-apiserver. All of these components are basically clients, and the API server is going to give us a record of these client interactions. In fact, we could often find various component interactions in the metrics as well, which are quite rich, and we're going to see some of these in our examples later on. We also have health endpoints. As you can see, there's 3 of them. And if you're wondering why we have so many, that's because until quite recently, the Kube-apiserver didn't ambiguate between kubeness, liveness, and readiness probes, and bundled everything up into a single endpoint, which was health-z. As of 1.16, the Kube-apiserver supports liveness and readiness as distinct health checking mechanisms. The Kube-apiserver can also be introspected using audit logs, depending on your cluster configuration. While this is technically a security feature, audit logs tend to be a terrific source of request information because they are structured, unlike our Kube-apiserver logs. So if you want to query about request information, it's going to make your life a lot easier. Our next incredible source of cluster information comes from etcd. etcd is different from other Kubernetes components in a number of ways. First, it's a third-party component, which isn't created from Kubernetes proper, and it's basically vendored in. For those of you who don't know about etcd, I'll just briefly describe it. etcd is the persistent storage litter for Kubernetes control plane. It's a distributed key value store, and it uses the Raft algorithm to provide strongly consistent views of data stored across its members. So that's what I like to call the elevator description for etcd. But more importantly, etcd is a database. It stores data. It stores specifically data about your cluster. So if you want to look at what happened in your cluster, this is going to be a tremendously powerful tool for you to look at when you're trying to figure out what's going on. So here are some ways that you can actually look at etcd. The first two items in the list are tools which allow you to directly access data from etcd. etcd-cuddle is the one people are probably most familiar with, which is a command line client for interacting with etcd. It's super useful for ad hoc exploration of etcd data. The second one is Augur, which is probably a lesser known tool, but it shouldn't be. It's a tool written by one of my friends and colleagues at Google. His name's Joe Betts. And Augur, the thing about Augur is that it can interact with a BoltDB file directly. This is super useful because this means you can query for data without actually having etcd running. And that in and of itself is valuable enough to justify using it. But that's really not all there is to Augur. Augur was specifically built to interact with Kubernetes etcds, which means it knows how to decode Kubernetes objects. So if you've ever used etcd-cuddle to try to look at a Kubernetes object, you'll see that you'll end up with a screen of jarbled protobuf. It's basically terrible. Augur can help you actually read that data. Anyway, with etcd, you also have metrics, which has a ton of useful stuff like compaction and snapshot and latencies. And it also has a health endpoint. Since etcd isn't from Kubernetes proper, the health endpoint doesn't really conform to the same format, and you'll get JSON output back from this health endpoint. And everything else in the Kubernetes control plane kicks back plain text. You can also look at the logs, which has its own unique way of marking severity levels. It's going to look a bit different than your other Kubernetes components. So now that we have this context, let's see how we can apply this in the wild. Elena, would you mind walking us through the first example?
Sure. So Han and I will show you a number of different examples to showcase how we can use the different metrics and tools we've shown you in order to debug some common cluster issues. I've mentioned this scenario a number of times because it's just so common. So let's work through this problem. A node has gone offline. I might find out about this in a number of different ways. I see that a node is reporting not ready, or maybe the pods scheduled on a particular node are showing unknown status. How might we detect this, given the metrics we have available? Well, here's a sort of obvious solution. Look for all the nodes that Prometheus failed to scrape. Here we use our favorite Prometheus time series, up. Since 1 indicates a scrape target is online, this query detects all nodes that are offline. We could use this query to build automation to check for nodes in this state for some period of time and perhaps automatically reboot them, so a human doesn't have to intervene on node failures or really think about them at all. Of course, usually things don't fail in such a tidy way. In production, I'll often encounter gray failures, where users complain their pods aren't working quite right. So I do some investigation, and I find that all the affected pods happen to be scheduled on a particular node, so we can isolate that as a likely source of the problem, but the node hasn't gone offline, so it wouldn't show up in our previous query, and we're not quite sure what's wrong. Poking around at some of the Prometheus metrics, I noticed that commonly, when a kubelet is in a gray failure state and is acting slow, it's slow for everything, not just pods and users. So this shows up in our Prometheus scrape duration data. In this case, we can detect such problems by looking at unusually high scrape time. Typically, it takes under a second to scrape data for a node, so if the node metrics endpoint is regularly taking more than 2 seconds to respond, there's probably something a little off. This query can help flag nodes that are not behaving optimally. Both of these examples used knowledge of how Prometheus works and its automatically generated time series to help us debug cluster issues. Prometheus knows whether or not it can successfully scrape a target, and it knows how long it took to scrape that target, so we can use that information to our advantage. Here, we don't rely on any innate knowledge of how a node works to detect these issues, so this is a great example of how you can do black box debugging with Prometheus.
OK, so now we're going to go over an example which is quite near and dear to my heart, because it's emerged out of the sweat, blood, and tears of not just myself, but a number of engineers over at Google, not just once, but a number of times in varying incarnations. So we're going to start with a crash looping API server. So this is a pretty common failure mode, which we should realize at this point because we know that the kubelet is going to try to restart broken containers. In this case, Kube-apiserver is unhealthy and it's crashing for some reason, and the kubelet is restarting it. So how are we going to figure out that this is happening? Hopefully, we can become aware of this before someone tells us that it's happening. So one option, since the Kube-apiserver exposes a public API, it's possible to set up uptime checks against the health endpoints to generate some picture of availability. This is pretty common. Alternatively, we can ingest metrics from the master kubelet, which exposes counters for liveness and readiness probes of the containers of the pods it's watching. In this case, the master kubelet is watching our Kube-apiserver. It's going to look something like this. And as a disclaimer, I've stripped out some of the labels to make it easier to parse on screen. The basic idea is you can set up a chart to display some of this information, much in the way that Elena had described earlier, and configure some alerting to ensure that the number of failed probes doesn't exceed some pre-configured threshold. So at this point, we've detected that our API server is crash looping, but we need to ambiguate between one of two situations. So is the kubelet trying to start a container when it sees that the container isn't running? Or is it killing the process and trying to restart it? In the first case, the kubelet is just in repair mode. It sees that a container which is supposed to be running isn't, so it just starts the container initialization process. In the second case, the kubelet is killing the process. In the case of a master node, this means that the liveness probe has failed enough times consecutively to trigger a kubelet restart. So how can we figure out whether it's the former or the latter? There are a number of different ways. We can look at the failure count in our metrics probes endpoint that we looked at earlier. Possibly, we can verify this by examining the kubelet logs, and because it will tell you if, in fact, the kubelet did drive a restart. In our case, it's going to turn out that the liveness, it was a failure in the liveness endpoint. We did have consecutive failures, and the kubelet was actively killing our API server process and restarting it. We can further investigate by curling our API server health check endpoint and passing in a verbose flag. This allows us to see all of the individual health checks configured for this health endpoint. And as you can see here, the API server health endpoint is comprised of a number of more granular health checks. And I bolded the one which is failing, which is the etcd health check. Since the kubelet is using this endpoint for liveness probing, that basically means if etcd is not healthy, our API server is actually going to be crash looping. So it turns out that our example isn't actually an API server issue after all. It's an etcd issues. And the slides from this point will reflect that. But now that we know it's an etcd issue, let's dig. One of the first things I do when I am debugging an etcd issue is, interestingly enough, I look at a Kube-apiserver metric. Specifically, I look at the etcd object count metric. This metric will tell you the number of objects that exist for a given Kubernetes resource. And believe me when I tell you it is not uncommon for random third-party libraries that you install in your cluster to create a bazillion objects. So in this particular example, there are a million such objects. And This can be more or less problematic depending on the size of the object. Let's say that the average object size for this CRD is about 1 kilobyte. Doing some math, if we have 1 million such objects, that's going to take about a gig of space. If the average size is larger than that, we really have a problem. Why? Because as we can see here, that the default size for etcd is actually just 2 gigs. So just looking at this one metric can give us a huge hint at a potential problem, which is memory pressure issues. Recently, we ran into a far more insidious variant of this issue. So let's take a look at these 2 metrics. The first one is the etcd count metric, and you can see that there's only one instance of this object that exists. The second one gives us a count of the number of updates for that specific resource. So there is one object, but it has been updated 1,200 times. So why is this a problem? So if we want to correctly model this in our heads, we have to take a step back. We need a proper mental model of how etcd stores data. So here we have a datum, some object that we store in etcd. There's an obvious dimension that we think about this, which is the size of that piece of that object. But etcd is a database. It doesn't store just one object. It's a key value store. It stores an object for each key. There are many objects. So we can see that we have this other dimension. But if we were to take the average size of objects and multiply it by the object count, would that give us an approximate size of the data used by etcd? And the answer to that question is no. etcd provides a watch mechanism so that subscribers can see changes to objects over time, which means etcd must store a historical record of changed objects. So if we revisit the metrics from the last slide, we can see that while there's actually only one instance of that object, that 1,200 writes to that object means that there's actually 1,200 versions of that object. So it's quite a bit different than what we initially thought. So even though we have 1,200 objects, we also now have to consider the size. So let's just consider, for instance, that the size of this object is large, say 200 kilobytes. Let's do some math. So 200 kilobytes, let's say API server is crash looping once every minute. So we have 1,200 writes in a minute. That's roughly 20 writes a second. So if the size of the object is 200 kilobytes, then that's 4 megabytes a second, or 240 megabytes a minute, which is about a quarter gig a minute. Now, etcd compacts every 5 minutes. So by the time compaction occurs, we have accumulated over a gig of data, which is problematic when you, again, consider the default etcd database size, considering that you are probably going to have other stuff in your etcd besides just this one object. So then what we really need to be able to do is ballpark the size of the object. If you can catch the API server while it's healthy, you can use kubectl. But in our case, etcd is actually not healthy, and the Kube-apiserver is not healthy. So this is when it becomes super useful to use Augur, because you can operate on the boltdb file itself. And that's how you would approximate the size of an object using Augur. So in the nasty variant of this case that we encountered recently, it turned out that this custom resource had a number of base 64 encoded images embedded into the annotations field, which drastically bloated the size of this object. There was also a custom controller which was going rogue, updating the object due to a bug in the equality comparison operation for the CRD. Basically, there was an unordered list which was always returning as unequal, so the controller would make an update request because it thought the object had changed. So this high write rate led us to bump into I/O throttling limits. But we were able to mitigate this by contacting the CRD owners and getting them to reduce the size of the images that they were storing. So the moral of the story, probably don't store images in your CRDs. If you have to, try to make them as small as possible. Ultimately, we got the custom controller fixed, which completely resolved the issue, leading us to our happy ending. Elena, would you like to walk us through our next example?
Yeah, last example. So, last fun problem. For a period of time, I had an issue with API server access being slow, both via kubectl and API calls. Now, the API server collects metrics for this, so I figured I'd dig into that to see if there was any wisdom I might gain. Perhaps a particular verb was slow, like post or patch, and that might indicate some issue with write performance. So this query allows us to plot out HTTP call latencies grouped by HTTP verb, and see if there's anything particularly slow. So here's that query plotted in Grafana against a production cluster, representing P99 latencies of the API servers by HTTP verb over a 24-hour period. The green line is a marker for 5 seconds, and this graph has a linear scale. It looks like there was a big spike in post latency towards the left, well over 5 seconds. Now, you may notice something a little fishy about this data. If I look at the max and current values of most of the verbs in the legend on the right, the current HTTP latency clusters just below 125 milliseconds. That's pretty slow for an HTTP call, and also kind of a weird number. The second thing you may notice is the maximum recorded HTTP call latency is exactly 8 seconds. Again, weird number. So I dug into this, and things got even stranger because I noticed that the histogram metrics being exported did not match the summary metrics within orders of magnitude sometimes. And it turns out that the default API server histogram metrics in Kubernetes were total nonsense because the min and max bucket sizes were 125 milliseconds and 8 seconds. So I dug into the code at some point to confirm this, and here is that code with a fix to add better bucketing sizes between 50 milliseconds and 60 seconds instead of 125 milliseconds and 8 seconds. After getting involved in upstream and voicing concerns around problems like this, the fix landed in Kubernetes 1.14 as part of the metrics overhaul enhancement proposal I helped write. So, while that query didn't help me pinpoint the source of the API server slowness, it did help me confirm that things were slow, and I was also able to confirm the issue and suggest improvements upstream. Which is a good opportunity for me to jump into talking a little more about upstream. In our last example, we saw there was an underlying issue with a metric that was providing bad data to cluster operators and made it difficult for us to figure out what was going on. How does SIG instrumentation address these sorts of problems? Well, it's a bit complicated. Updating metrics between releases could break monitoring stacks. For example, fixing the API server latency buckets meant that users would potentially see wildly different performance metrics between a 1.13 and 1.14 upgrade, despite the actual performance not necessarily changing. This could result in anomaly detection throwing incorrect alerts between releases. And there are other issues beyond the metric data itself. If a new metric is added that causes a memory leak or generates too many time series, there's no real way to disable it, meaning a full bug fix and cluster upgrade rollout needs to be performed when bad metrics are discovered. So how can we coordinate developers to address this and ensure that end users are fully informed about these sorts of problems? SIG instrumentation has spent a lot of time identifying and cataloging broken metrics, like in our API bucketing example, but that's not the only one. For example, the labels on cAdvisor metrics did not match the Kubernetes instrumentation guidelines, so they couldn't be joined with other Kubernetes metrics, like those exported by kubestate metrics. There were also a number of time series that used the wrong data types. For example, kubelets were only exporting pod start time in summary form, meaning you could not aggregate pod start times across a cluster in order to rank pod latencies by percentile. You need a histogram for that. There were also issues with unit standardization. Some time series were in microseconds, others were in seconds, and in some pretty bad cases, they claimed they were in seconds when they actually were in microseconds. This did not conform with Prometheus and Kubernetes best practices for unit normalization. So we put together a KEP detailing the problems, and we fixed it. Most of those fixes rolled out in the 1.14 release. Now, for some metrics, we could follow an informal deprecation policy. For example, marking the time series with non-standard units as deprecated in their help text and in the code, and adding brand new time series with the correct units. But others, like API server bucketing, need to be updated directly. This might cause confusion to end users of those metrics. So how do we communicate that those metrics are deprecated and ensure users are able to smoothly transition off them? For these purposes, SIG Instrumentation has developed a metric stability framework, and we're working to transition all Kubernetes control plane metrics to use that framework. The metric stability proposal will allow us to treat metrics as a proper API and with an enforced automated multi-release notice period for changes to stable metrics. It will also allow us to slowly phase out obsolete metrics across releases before deletion, and most importantly, it will provide tooling to enforce stability, for example, via static analysis. In practice, what this means is we've replaced all direct use of Prometheus metrics with a component-based wrapper, which allows us to annotate metrics with a stability level and deprecation status, like you can see in the code on the screen. So it's a great first step that we now have the capability to mark metrics as stable or deprecated, but there's still a bunch more implementation to come. Now that we have the metric stability framework in place, we need to decide what metrics should actually be considered stable. And to accomplish that, we need to develop criteria around what constitutes a stable metric and select some metrics to be promoted to stable. We'd also like to add flags to the various Kubernetes components to allow for disabling individual metrics at runtime so that if a new alpha metric causes stability issues by leaking memory or having cardinality explosions, we can just turn it off rather than having to do a full bug fix rollout. You may have noticed we didn't discuss tracing in this talk, and there's a SIG instrumentation cap under consideration for adding distributed tracing support to Kubernetes components. And as of last Friday, a new cap was also proposed to add structured logs to all Kubernetes components, which is a thing I have been asking for a year. And finally, we have more metric improvements in the pipeline as we continue to identify suboptimal metrics and iterate on them. So, if you want to learn more about any of this, we invite you to attend the SIG Instrumentation intro and deep dive sessions, which are scheduled in the next slot today and the same time slot tomorrow. And I think we don't have time for questions, but you can come find us after the talk. Thank you, everyone.